All right. So, yeah, so today we're going to be going through the paper um, that we worked on recently called Robust Speech Recognition for Jamaican Patois Music Transcription. And as the name suggests, we essentially just we developed some speech recognition models for Jamaican Patois. So, at the heart of the paper, what we did was we at the heart of the paper, what we did was we created a data set of Jamaican Patois music. So we curated a data set of that consisted of about 40 hours of Jamaican Patois music. And then on top of this data set, we use it to fine tune some state of the art speech recognition models. And then based on that, the results we got from that, we developed some scaling laws that predicted the performance of the whisper models on Jamaican Patois audio. So this paper is going to this paper essentially describes how we did that at the so the motivation for the paper was essentially that we realized that Patois, like Jamaican culture is really prevalent. Like if you go anywhere in the world and you tell people that you're Jamaican, they'll probably know what Jamaica is. And that's something that can't be said for a lot of countries. And but despite this, even though AI models like ChatGPT can generate Patois text, if you've ever been on YouTube, for example, and if you've ever been on YouTube, for example, and tried to read the captions on some audio that was Jamaican Patois, the results have never been good in my experience. So, especially in music transcription, if you've ever listened to a music video and turned the captions on by accident, a lot of times you just see the dashes to indicate that it doesn't really know what word to assign it to or something like that, or the transcription is just completely wrong. So we wanted to kind of attack that problem and develop a system that can convert speech into text for Jamaican Patois and do so really reliably. So like I said before, to do this, we introduced a data set of about 42 hours of Patois music and its corresponding transcriptions. Then we use that data set to fine tune a series of whisper models. And then we develop some scaling laws that model the ASR performance as a function of the data set size and model capacity. So this section of the paper just talks a bit about some related work. So we won't really dive too much into it. But so first, let's talk about the problem at a technical level. So essentially, the problem that we're trying to solve is if we have some audio clips, represented by in this data structure, and the corresponding transcriptions of each of the audio clips, we want the AI to learn a function that maps the audio to the text with a high degree of accuracy. Right. So that's essentially what speech recognition is. It's the task of converting speech to text with high accuracy. So the data set that we collected consisted of about 5,100 recordings of Jamaican Patois music, along with the transcriptions. Each data point, we realized that there could be some potential legal implications if we directly release the audio as well as the text. So to work around that, what we did was in the data set, we included the URLs to the audio and transcriptions of the audio itself. So the audio itself was sampled at 22,050 hertz. So in each recording, we had over 600,000 samples. So in total, this mapped to 42 2.58 hours of audio. And as far as we know, this is the largest data set of its kind. This is the largest data set that of patois music, of transcribed patois music at least. And so initially we annotated the data by hand because, initially we annotated the data by hand. But in the future, one of the things that we want to work on is developing a way to automate that annotation process, right? And then, so that's essentially all we really said about the data in the paper. But to do the fine tuning of the model, we used the OpenAI Whisper models as the base. And we chose Whisper because they achieve state-of-the-art performance on speech recognition or speech-to-text modeling. So Whisper models were trained on 680,000 hours of audio, and that kind of enabled them to learn really robust audio representations. So we use them. We use the Whisper models because these features should facilitate the effective adoption of, like, effective transfer to Jamaican Patois. Because Patois is somewhat similar to English, we kind of felt that since English was the main language that was used to train Whisper, then a model that was really good at English would be able to learn to transcribe Patois really well. So some limitations that we noticed with the Whisper models, we noticed that there were five variants of the Whisper: the tiny, the base, the small, the medium, and the large variant. But we only fine-tuned the tiny, the base, the small, and the medium variants because we didn't have the compute resources necessary to fine-tune the large variant of the model. So this section 4, kind of details the results that we got, how we set everything up, and we talk a bit about how we developed how we evaluated the scaling performance of these models. Oh, by the way, if you have any questions, just feel free to stop me at any time.
Yeah, I have a bunch of questions, but can't wait.
All right, cool. So, so for each of the Whisper models, the tiny, the base, the small, the medium models that we trained them on 20 hours, 35 hours, and 40 hours of audio each. So all in all, so there was the tiny, the base, the small, the medium, and then we trained each of them on 25, 35, and 40 hours. So 4x3. So all in all, we trained 12 different models. So we did this to you'll see why we did it later, but it will help us to develop the scaling laws or scaling characteristics of the models. So to train it, we use the Adam W optimizer, and we use a learning rate of 1 e to the minus 4 or e to the minus 5. So during training, we varied the learning rate with a linear learning rate schedule that had a warm-up phase of 500 steps. And we did the training for 4,000 steps in total. So for each of the 12 models that we trained for 4,000 steps. So before the fine-tuning, earlier I mentioned that when we collected the data set, the audio was sampled at 22,050 hertz, but we had to downsample that to 16,000 hertz because that's what the Whisper model expects to get as input. And then another detail about the Whisper model is that before it doesn't just ingest the raw audio, it ingests what's called log-mil spectrograms. So for each of the audio samples, we had to convert them into the spectrograms before we pass them as the input to the model. Yeah. So to evaluate the quality of the model, we used what's called the word error rate. And how that's measured is if you have a sentence with, let's call it 5 words, 1, 2, 3, 4, 5, right? And then the AI model predicts 1, 2, 3, predicts 1, 2, 3, 4 words correctly, and it predicts this word incorrectly. Then the error rate is the amount that it got correct divided by the total amount of words, essentially. So that's how the word error rate is measured. It just measures the amount of words that it measures. Wait, actually, that's wrong. The error rate is the amount of words that you got incorrect divided by the total amount of words. So it measures the amount of errors that occurred in the transcription. So as you can see, while we were training the model, we measured the error rate. And you can see that for each of the models that we trained, the error rate was going down pretty steadily. And like as you'd probably expect, the best model performance was obtained from the biggest models. So you can see the medium model, which is the biggest of the models that we trained, it had the lowest error rate, while the tiny model had the biggest error rate out of all the models that we trained. So now these are the results of the models of the trainings that we did. Yeah, so as you can see here, we trained the tiny, the base, the small, the medium. We trained each of those models on 20 hours, 35 hours, and 40 hours of audio, respectively. So, as you'd expect, the tiny model doesn't really do very well. Like the lowest error rate that it got was 70%. But the medium model ends up doing a lot better, with the best error rate that it gets being 30%. Now, 30% isn't great, but the biggest whisper model that was ever trained got an error rate of 89% on Jamaican Patois audio. So, like, even fine tuning on our data set on the smallest model available gives better performance than the baseline best whisper out there. So, yeah. So now we want to talk about the scaling characteristics of the model. So what the scaling characteristics do is it kind of, scaling laws give you a mathematical way to predict how well a model is going to perform, given the size of the model and the amount of data that we have available, right? So that's kind of what we try to do here. So to do that, we used we used this equation. We modeled the equation using like a power law function of both the model size and the dataset size. And then we took the logarithm of both sides to kind of give this linear relationship. So typically, like, you'd expect a linear function to look something more like y equal mx plus c. So you don't expect it to have two terms. But if you model the two terms as a matrix, so you'd let m be the alpha and the beta. So m would be alpha comma beta. It would be a 1 by 2 matrix. And then x would be the log m and the log d. So you'd have log m and then log d, which is a 2-by-1 matrix. If you multiply those two together, if you multiply m, if you do a matrix multiplication, your output is going to be a 1-by-1 matrix. And then log alpha is 1-by-1. So 1-by-1 plus 1-by-1 gives you 1-by-1, which is what you get which is why you'd get a single value for the word error rate here. Yeah, so we use this formulation, but we represented it as a matrix so that we could run a linear regression on it. And so once we did that, it gave us the parameters A, the parameter alpha, and the parameter beta, which you can see here. So log A got mapped to 5.06, alpha got mapped to 0.255, and beta got mapped to 0.269. And when we converted that back from the log into the normal representation, it left us with this final equation. So to kind of verify that the equation works, what we did was for each of the model sizes and the data set sizes, so for each of the model sizes M and the data set sizes D, we plotted the value that we got for the word error rate when we tested it. And that gave us this graph here. Yeah, that gave us this graph here, right? So if you look here, for example, let's see. Yeah, so if you look here, for example, the medium models would correspond to the medium-sized models would correspond to these three dots right here. So when we use 20 hours of audio, it would have given, on a medium model, the scaling equation predicts that we would get about 0.38 or 0.37 as the word error rate. And you can see that when we actually ran it for 20 hours of audio, the actual word error rate that we got was 0.4. And then when we ran it with the medium model on 40 hours of audio, you can see that it predicts that we'd get about 0.31 for the word error rate. And here it predicts, and here when we actually ran it, we got 0.30. So if you look at the scaling chart and the actual experiments that we ran, the numbers match up pretty well. So if you notice over here, we have an extra set of points, because these points map to the tiny model. These points map to the base. These points map to the small. These points map to the medium. So these points would map to the large. So even though we couldn't train the large model by itself because we didn't have enough compute for that, we could still kind of predict how well the large model would do because we know that the rest of the predictions were pretty solid. But yeah, I mean, that's essentially all we did in the paper. So we, like I said, we just we curated a data set. We used the data set to train Whisper models, to fine-tune Whisper models. And then based on the results that we got from that, we developed some scaling laws to kind of predict how well the Whisper models would perform on speech recognition tests for Jamaican Patois music. So, like I said earlier, we kind of did this because we hope that it would really help to kind of advance the just the field of AI in Jamaica, and hopefully we can actually build on these kind of systems to actually develop useful speech to text systems for Patois. But yeah, so if you have any questions, that was a pretty good time to ask.
Yeah, this is great. Um, yeah, fine-tuning works and data is really important.
Mm-hmm.
I did have a couple questions. So like
Yeah, sure.
I was gonna ask what error rate you needed for production.
Yeah.
Um,
So um so typically for production, you'd want error rates of less than 10%. So the actual Whisper models, when OpenAI released them, the Whisper Large on English, it has an error rate of like 7%, I think. But when we ran it on Patois, on our Patois data set, it had like a 90% error rate. So we realized that even though it was so good at English, it was really terrible for Patois. Um, yeah. So when we kind of did the scaling laws to predict how much more data we would need um, to train bigger models to get to a stage where they would be ready for production. Basically, that's
yeah.
why yeah.
So yeah, it seems like based on the graph, the 40 hours should be enough with the large model to get to sub 10%.
No. So like if you look at it here, right? This is the 40 hours for the large model, and
Mhm.
it maps to something like 23% maybe.
Oh, that
Yeah.
looks sub 10 to me, but I get, yeah, I get
Yeah.
why.
Yeah, because
Okay.
each of these is a 10% increment, so 20% would be somewhere around here.
Yeah, I see it now. So some more data, but it
Yeah,
definitely seems achievable.
yeah.
Um,
So,
the other question I had was somewhere in the related work was a music content filtering system. Is
mhm.
this related to that or part of the like a component of that system?
Um, this thing?
2.5. Yeah.
No, it not directly. So not directly. I mean, it would be really helpful for a system like that because um, if you actually read the if you actually read the the paper, oops, yeah, if you actually read the paper, what they do is they use speech recognition systems to convert the music to text, and then they kind of clean it up, like for explicit language while it's in text, and then they convert it back to audio. So if you have something that's better at converting the patois music to text, then it would be really helpful for something like that.
All right, cool. The other question that came up in my mind was a fine-tuning and this concept of catastrophic forgetting that I learned about. Like, does the performance on English or other data sets fall off when you fine-tune on Patois, or do you guys plan to check that?
Um, I don't know. It's possible that it does fall off a bit because yeah, I mean it's definitely possible that it does fall off a bit. But if we're fine tuning it just to um understand patois, then I don't think that should be too much of a problem because we wouldn't be using it to try and understand any other languages.
Cool. Yeah, I figured. I was just interested. And I think the last question I had was the cost to do all of this with the creating of the data set and the training, the 12
Mm-hmm.
times.
Yeah. Uh. So. Hmm. I don't have a solid number, but I'm pretty sure. Hold on, let me think about this. Because I think that when we trained it, we spent about, mm, something like 12 US on compute in total. We spent something like 12 US in total for the
That's
compute that
that's
we
not
need.
bad.
Yeah, definitely
Yeah.
not.
Okay.
So, yeah, so like in the future, we definitely plan to um like retrain these with a lot more data and with the bigger models. We were using a server at the time that didn't have the capacity for the big models, so we're going to um retrain them with more compute and more data to see how much better they do.
Cool, cool. Yeah, this is cool. And then you have this data set, which is like, as you pointed out earlier, really valuable because for some reason, strange reason, Jamaica has a really big brand for this compared to the size of the country. So that data set does have economic value. That's
Mm-hmm.
good. Yeah,
Yeah,
this is pretty cool.
yeah. Thank you. Let me stop recording.
Hi, good evening.
Yes.
Hi. Hi, my name is Grace Solas. I joined late. I saw the invitation to join on LinkedIn. So I have
I,
a can you hear me?
yeah, I can.
Right. Yeah. I saw the invitation on LinkedIn. So I didn't actually get a chance to read the paper. So
Mm-hmm.
anything I ask maybe in the paper. So if you could just tolerate me for a minute though. And I'm just having a new and fresh interest in all of this.
Yeah, go ahead. No.
Um Currently doing an AI course myself. But question, my fascination with Jamaican Patois has to do largely with the fact that it has this variation depending on where in Jamaica you are. You have deep rural, and when I say deep rural, you're talking about, you know, St. Elizabeth, Manchester Patois sound different from St. Mary Patois, which sound different from St. Andrew Patois. So I'm just curious as to how does your work um address this or fits, how does this fit into your work? Does it um what is your well, I mean, I hear you mention about using the music.
Mm-hmm.
So I am taking it that your data set is entirely from recorded music. Is that where you
Yeah,
what is it you're doing?
that's
Okay.
correct. So to address your point, yeah, if we wanted to address more diverse types of pato, like Saint
Mm-hmm.
Mary pato or Saint Elizabeth pato, all that
Mm-hmm.
like the or approach is kind of generalizable. All we would need to do is collect data that is representative of those kinds of pato
Mm-hmm.
and retrain the models on it, basically.
Okay. Um, okay. So, and in terms of what you've done thus far, it is some in terms of the output from it, it's
Mhm.
something that could actually be used for closed captioning. Is that something that it would actually be you could actually use it for?
Yeah, that was one of the kind of motivations that we had for this. It's definitely
Mm-hmm.
not good enough yet to
Mm-hmm.
be used for closed captioning reliably,
Mm-hmm.
but yeah, it's not good enough yet. But if you were there when we were talking about the scaling performance, we kind
Mm-hmm.
of have an idea of how much more data we would need to train a model with to to get something that would be good enough to do closed captions on.
Okay. Okay.
Yeah, so that's something that we want to do in the future.
Okay. So in terms of your trajectory, in terms of usefulness, that's on the goal, on the milestone path.
Definitely.
Okay. What else is on the milestone path?
So we want to extend the work. So right now we focus on speech recognition, which is which is the task of like converting audio to text, right? But we want to kind of extend it to text to speech, where we would, like, if somebody types in patois text, we could generate something that sounds like an actual Jamaican talking to you, reciting, like the talk, like, sorry, talking about the text that dictating the text that the person wrote down. Yeah, so the next thing that we want to do after we get these models even better is to do some kind of text to speech and make it high quality.
Text to speech, text to speech. Okay, because that's another challenge with patois in terms of the actual writing of patois.
Yeah.
We are aware of the tons and tons of variability. And in
Yeah.
fact, if you look at something, a published work like the Patois Bible, for example,
Mm-hmm.
to me it appears to be such a it looks like more of a linguistic it's a highfalutin linguistic production in my view, versus how, if we were to sit and write patois ourselves, how we would actually write it.
Yeah.
I don't know, you're familiar with it? You're familiar?
I've read parts of it.
Right. So I
So
mean,
I've tried.
it sounds great, but I mean, obviously, to me, it's written by somebody who understands,
Yeah.
linguistics, as opposed to the majority of persons who would not, if you were writing Jamaica Patois, probably would not write it like that.
Yeah. So we've thought about that, and we are actually talking to some people from the team that wrote the Patois Bible over at UE.
Mhm,
But I guess what we want to do is just to collect as much data as possible, and
mhm.
because, like, if you've tried to read the Patois Bible, you know that that's not how, like, a Jamaican would, like, if they were texting, that's not how they would, like, spell out the
Yes,
words
it's
that
not
they're trying
one.
to say. So while we do want to try to capture that as well, like the actual the linguistically correct spellings, we also want to capture the ways that people would actually spell patois text if they were typing it out.
Right, right. And you're familiar with the Microsoft, like in Microsoft Word, you can actually use the dictate function, and you can speak, or you could upload a recording, translate a whole meeting using Microsoft Word. And
I didn't know that.
I actually just discovered it maybe about a month ago, and wish I had known this some time ago, because it's very helpful. You can actually even like this Zoom call that you're on now, if you wanted to, you could use the dictate function on it, and you could upload the recording of this meeting, and it could type the transcript for you. What I found is I had an interview with a classmate who is German, but she lives in the US, so her accent is very, you don't really hear a German or a US accent. It's a very interesting kind of you can't really discern where it is from. But her diction is it's very clear. All the words are very clear and very articulate, and you hear it so well. So when I use it to translate a meeting with her, it comes out wonderfully. But when I try to translate a meet, and it even gives you, speaker one, speaker two, so it labels who is
Mm-hmm.
speaking. And yeah, so I did it with somebody, so a family member. And because myself and my family member sound fairly alike, it didn't catch the difference of the whole thing looked like speaker one, because both of us sound alike, so it didn't pick us up that well. And also when we're throwing the pattern in there, of course, it got it got confused. So, but where I'm going with all of this is to say that in terms of the milestones, the fact that
Mm-hmm.
Microsoft actually has this feature, and I suspect that it probably it's not just English
Yeah.
that it can do. It can probably do some more of the, like the brick language, the languages of brick. If it is that we get to the point where we've gotten this sense of Jamaican Patois down to where you're obviously trying to get down the error rate. Maybe that's somewhere that you can use an established platform like that to make it even more accessible, useful without having to reinvent the wheel. That's really where I'm going. Because I'm saying it's already there. It's actually a thing.
Yeah.
That's actually in Word. It's already there.
That makes sense. I actually had no idea that Microsoft did that with Word.
Yeah, I just
So that's
discovered
really
it.
good to know.
Yeah, if you just open it and you look on you'll see something called Dictate. It's in Word. It's in 365. I don't know if it's in the other versions, but it's in 365. But if
Okay.
you make one there that you can use. Yeah. All right. Well, I'll look for the paper. The paper is available on your site. There's a paper available.
I'm not sure. If you do a Google search, you can find it.
Okay.
Yeah, I did a Google search before we started this meeting, and it was the first thing that popped up.
Okay. So your next milestone would be you just continue to build to gather data to perfect it or to reduce the error rate rather.
Yes, correct. So like I had mentioned earlier, like commercial speech to text systems, they need error rates less than 10%. So that's kind of the goal that we're aiming for.
Okay. And the solution for that really is just more and more and more data and more compute power.
Yes,
That's
exactly.
Okay.
Exactly.
Yeah, the text one really kind of beating me because, as I said, just the way how we write versus the things that are available. Because even if you look at Miss Lou's poems, because our language has been so it's so dynamic, even the things that she has written, if they were to be written today, I'm not even so sure if it would be written even with the same, if they would be written using the same syntax of yeah. I don't know how it would be written today. Bottom line, I don't know how we would write what she wrote then, how we would actually write it today. Some of it, even though when you hear it, it makes sense. You know exactly what it is. But when you look at the text, the combination of where you use a I versus a or a E and that kind of thing. That's the part that mesmerizes me. I don't know how we're going to solve that one. So yeah, there's the fact of we tend to add words, things that are in the moment, are the hot items of the day. They get added to the vernacular. They make up part of, and you find it in the music. You find it very, very quickly in the music. But it's the writing part that beats me. I just can't figure out how we're going to solve for that X. How you're going to get to that point where you get the writing to be something that is reliable. That you can say, yeah, it's really 10%. How you go is really less than how you gonna do that when that's something that's constantly changing. We can't even agree how to spell uno. People spell uno ONU. There is UNNH NNUH.
So one of the things that one of the big lessons that people have learned in AI research over the past couple of years is that methods that when you try to solve problems with data driven and compute driven approaches, they usually end up being more tractable that way than when we try to hand design systems that would learn for each little scenario that we can think of. So essentially what I guess the best way to like approach those problems is to just throw as much data as we can at the problem and have the AI learn to make those associations between all the different spellings and all of those things. Because there has
Yeah.
been research shown that multiple different semantic spellings of words can activate the same internal representations in an AI model. So if you throw enough data at the AI, it can learn that stuff.
Yeah, that's good to know because on the back of that is my concern about subjugating the culture. You know, we're going to leave out some things because AI can't handle it, so we just automatically leave them out, and then after a while, you end up with a relevance problem on your hand. So it's good to hear that that is really, you know, that's doable.
Yeah.
But not to be forgotten is just making sure that we don't, box the culture into whatever AI can handle. Because AI is until we're not at general intelligence, and even then, it's still something that requires human input and human um, yeah, speech evolution, um, vocabulary evolution, and so on. It still requires that. So we would want to be in a state where we are, boxing our culture, which is just inherently very dynamic.
Yeah.
It's just
Yeah, I agree.
part of the culture is to be dynamic. So yeah, well, yeah, I'd keep my interest and look out for what else is there.
Thank you.
Thank
Does
you.
anyone else have any questions?
Oh, I had one I forgot to ask, which was the plan to automate dataset creation.
Yeah. So basically how that would work is so if we want to automate audio dataset creation, it's essentially just getting a system that's really good at converting the speech in the audio into text, right? So right now we don't have any systems that are good enough to do that for Patois reliably yet. So we can make it easier for human labelers by having the AI generate transcriptions and then having the humans only correct the transcriptions. And we can use that to build up more and more data to retrain the AI. And eventually, if you do that over and over, in theory, the AI should get good enough to do the transcription itself without making too much mistakes.
Okay, that's fair. That makes sense.
Yeah.
All right, that's it for me. Thanks.
All right. Nice. Anything else? All right. Well, if there are no other questions, we can end the meeting here. Thank you guys for coming out.
Thank you.